In the world of chemistry, not all breakups are created equal. Today, we're diving into how chemical bonds decide to, well, call it quits. And it really is a story of clean splits versus some pretty messy divorces, all happening at an atomic scale.
So let's just jump right in with a big question. We talk about chemical reactions all the time, but what's really going on when that fundamental connection between two atoms just snaps? How does a bond actually break?
Okay, check this out. Our guide for this entire journey is this one single page of chemistry notes, and it lays out two totally distinct ways that a covalent bond can break. You can think of it as a nice, amicable split versus a super messy, dramatic one. So let's decode these notes together.
At the very heart of any covalent bond, you've got shared electrons. That's the whole deal. So it makes perfect sense that when that bond breaks, a process chemists call fission, the big difference between the two breakup styles boils down to one simple question: who gets the electrons?
First up, let's talk about what we can call the even split. This is the clean one, the fair one, the amicable breakup. Both sides just walk away with exactly what they brought into the relationship in the first place. And in chemistry, we call this fair split homolysis. Okay, so let's get a little more specific. Homolytic fission, or homolysis, is when that shared pair of electrons splits right down the middle. Perfectly. The covalent bond breaks in a way that each atom takes back one of the shared electrons. It's totally symmetrical.
And in the language of chemistry, this is what it looks like. That line between A and B, that's their shared pair of electrons. After the split, boom, they go their separate ways. And that little dot on each one, that's super important. It represents the one electron that each of them took back.
So what do we even call these things with the single dot? They're not ions, right? Because there's no charge. They're actually neutral species with this unpaired electron, and we call them free radicals. And because of that lonely, unpaired electron, they are incredibly reactive, always on the hunt for a new partner.
So what kind of conditions make this even split more likely? Well, it usually happens when the two atoms have a really similar pull on electrons. That's a property called electronegativity. So when that pull is evenly matched and you add a big jolt of energy, like super high heat or some UV light, the bond is way more likely to snap symmetrically.
And now for the drama. Our second type of breakup, the uneven split. If homolysis was the friendly parting of ways, this is the messy one. This is where one partner walks away with everything, leaving the other with absolutely nothing. In chemistry, we call this heterolysis.
Yeah, heterolytic fission is just fundamentally unfair. When the bond breaks, one atom is just plain better at attracting electrons. It's more electronegative. So that stronger atom doesn't just take its own electron back. No, it takes the entire pair for itself.
And the chemical notation here tells the whole story of this little electron theft. Atom A now has both electrons, see the two dots, which gives it a negative charge. And poor atom B is left totally empty-handed. And without its electron, it's left with a positive charge.
So you see the difference? With the even split, we got neutral free radicals. But this unequal split creates charged particles called ions. And if the atom that stole the electrons is a carbon, we call it a carbanion. The one that lost the electrons is a carbocation. The bottom line is, heterolysis creates charges.
So what's the #1 factor that pushes a bond toward this messy breakup? Well, it's a big, significant difference in electronegativity. When one atom is pulling on those shared electrons way more strongly than the other, it's pretty much guaranteed to eventually just take them completely.
All right, we've met our two breakup styles. Now let's put them head-to-head in a direct showdown. This will really lock in the differences between them.
This table just sums it all up perfectly, doesn't it? For homolysis, you get that even split which produces neutral free radicals. And this happens when there's a low electronegativity difference. For heterolysis, it's an uneven split creating charged ions, all because of a high electronegativity difference. And these lead to totally different kinds of reactions, free radical mechanisms versus ionic mechanisms.
Now here is a super important detail from our notes. It says that breaking a bond heterolytically, the messy, uneven split, always takes more energy. So you have to ask, why is that? Well, it's because after you split the bond, you then have to physically pull a brand new positive ion away from a brand new negative ion. And believe me, they are desperately attracted to each other.
And this simple chart just makes that point visually obvious. The energy barrier for homolysis is pretty high, sure, but the energy you need for heterolysis is way, way higher.
It's all because of that powerful electrostatic attraction you have to overcome.
Okay, so we've seen the two ways a bond can break apart, an even split or an uneven one. But so what? Why does this fundamental choice actually matter in the grand scheme of things?
Well, it matters because everything that happens next depends on it. Knowing how that bond breaks is the absolute key to predicting what new bonds are going to form. The nature of the breakup literally sets the stage for the entire chemical reaction that comes after.
And these are the two paths, the two destinies. The even split homolysis gives you those superreactive free radicals. They kick off chain reactions, which are involved in everything from how plastics degrade in the sun to the process of aging. The uneven split, heterolysis, that gives you ions, and those drive the ionic reactions we use to build complex medicines and new materials. These two mechanisms are the starting point for making almost every molecule we use every single day.
Which leaves us with a final, really big thought. We've just decoded the basic rules of the chemical breakup. So if we can understand the conditions and we know the properties of the atoms involved, does that mean we can actually predict and maybe even control the outcome of any chemical reaction? That question, well, that's what drives all of chemistry.